Good day everyone. My name is Kanak and I am an application engineer at Netsim. Today I will be focusing on simulation of vehicular ad hoc networks using Netsim. In this webinar, we will be talking about VANETs, Traffic Simulator Sumo, which is an open source tool, and interfacing Netsim and Sumo. We will start with a quick introduction to vehicular ad hoc networks, which are an extension to VANETs. Next, we will talk about the Traffic Simulator Sumo. Then we will show you how to interface Netsim with Sumo for running VANET simulations. In the end, we will provide an understanding of various research areas in VANETs and future development of VANETs in Netsim. And finally, we will have a QA session to answer your questions. I request everyone to ask their queries at the end of the demonstration. We are currently muting all participants and you may write your queries in the chat box. Vehicular ad hoc networks are a subset of mobile ad hoc networks of MANETs. A mobile ad hoc network, MANET, is a continuously self-configuring infrastructureless network of mobile devices connected wirelessly. Each device in a MANET is free to move independently in any direction and will therefore change its links to other devices frequently. Each device must also forward traffic unrelated to its own use and therefore be a router. The primary challenge in building a MANET is equipping each device to continuously generate and maintain routes required to properly route traffic. Now, vehicular ad hoc networks are used for communication between vehicles, V2V, and infrastructure or roadside equipment, V2I. VANETs can use any wireless networking technology as their basis. The most prominent are short-range radio technologies like WLAN, either standard Wi-Fi or the vehicle-specific IEEE 802.11p. In addition, cellular technologies like LTE or WiMAX can support VANETs. In Netsim, VANET simulations are based on the 802.11 standard. Moving on to the components of VANETs, the main components of VANETs are the vehicles with their onboard unit, OBUs, and the roadside units, RSUs. OBUs follow ad hoc communication and can be used to get the vehicle's position, predict driving behavior, and detect traffic violations. Additional functionalities can be added to the OBUs. For instance, traffic information about road conditions ahead or alerting emergency services in case of an accident. The RSUs are stationary units located on the roadside that provides connectivity support to passing vehicles. RSUs can follow both ad hoc and WLAN communication. In Netsim, both OBUs and RSUs can be configured. Here you can see a screenshot of a Netsim simulation with OBUs and RSUs. This network scenario involves 5 vehicles having OBUs and an RSU. Moving on to the applications of VANETs. Applications of vehicular ad hoc networks are categorized into 3 major groups as commercial-oriented applications, convenience-oriented applications, and safety-oriented applications. Safety-oriented applications look for increasing the safety of passengers by exchanging relevant information via vehicle-to-vehicle V2V and vehicle-to-infrastructure V2I communication. And commercial and convenience applications improve passengers' comfort and traffic efficiency. Currently, Netsim supports only regular communication and safety messages are expected in our next release. Now, we will talk about a traffic simulator named Sumo, which is the short form of Simulation of Urban Mobility. Sumo is a free and open traffic simulation software which is available since 2001. Sumo allows modeling of intermodal traffic systems including road vehicles, public transport and pedestrians. Included with Sumo is a wealth of supporting tools which handle tasks such as route finding, visualization, network import and emission calculation. Sumo can be enhanced with custom models and provides various APIs to remotely control the simulation. Some of the areas of research using Sumo are evaluating applications in an online loop with a network simulator, evaluate performance of traffic lights, evaluation of eco-aware routing, investigations on network-wide influences of autonomous route choice, evaluating the performance of traffic surveillance, etc. I will now show you the GUI of Sumo. Here is the GUI of Sumo, and I will now open a Sumo configuration file. Shown is a typical network with roads, junctions and vehicles. This scenario has 7 edges or roads interconnected at 6 junctions, out of which 4 have traffic signals for monitoring speeds and controlling traffic. Here is a traffic light and you can see red and green lights. Users can see the effect of green or red lights during the simulation. The Sumo GUI provides options to set delays between simulations for easy visualization. I am now setting the delay to 1000 milliseconds. And I will now play the simulation. Users can zoom in and out of the scenario and also see the movements of vehicles, which are shown as yellow triangles. Users can also pause the simulation and also progress the simulation in steps using the step button. As you can see, the vehicles will stop at the red light in the central junction. When the light turns green, the vehicles continue their movement. Let me pause this for a second and change the vehicle icon to resemble a car. For this purpose, I will now set the simple shapes and modify the vehicle size. This is for better visualization. And I'll play the animation. Multiple views are also available to zoom into different sections of the network. For inputs to Sumo, we need a network file which contains the definitions for creating map, traffic lights, nodes, etc. The network file is in turn created from a node file and a edge file. The node file defines nodes or junctions, which are basically the intersections. And the edge file defines the connections between them, which is basically the roads. A vehicle file which defines road paths that each vehicle will follow, and a configuration file which specifies network and route files used as input and the simulation time. Sumo outputs a mobility file which is used as input to Netsim. These are the steps followed to obtain the mobility.txt file from Sumo via command line. I will now open command prompt and show you how these commands actually work. The first step is to change the current directory to Sumo binary folder. For this purpose, I will now execute the command cd space the file path of the Sumo bin folder. Next is to provide the Sumo configuration file as input to the Sumo command and in turn get a Sumo trace file as output. As you can see, I have used the Sumo command and passed the file path of the configuration file and in turn obtained a Sumo trace file, which I will show you. As you can see, a Sumo trace file has just got created. The next step is to change the current directory to Sumo tools folder. Followed by this, we pass the sumo trace.xml file as input to the trace exporter and obtain the mobility file as output. As you can see, a mobility file has just got created. Netsim has a particular format for the input mobility file and the output from Sumo is slightly modified to match Netsim's mobility file format. As per this format, we initially specify the number of nodes in the scenario, which in our case is the number of vehicles in Sumo. And we also specify the environment size. Secondly, we specify the initial positions for each node in the network scenario. And thirdly, we specify the positions of each device with respect to time. I will now open the mobility.txt file. As you can see, the number of nodes is 5, which corresponds to 5 vehicles in Sumo. And the X and Y grid lengths are specified as 500. Then we have the initial positions of each device sequentially, followed by this is the corresponding position of each vehicle with respect to time. For instance, at time 5.0, device 1 was at position X 1.65, Y 186.35 and Z 3.47. Now, we are done with the process of creating mobility file and we place the mobility file in the bin folder of Netsim. After that, for starting the simulation, we need to open Netsim. Basic users are encouraged to try the GUI version first. Let's have a look at the VANET simulation of the equivalent network in Netsim. For this purpose, I will now open a network scenario that we have already created. To create an equivalent scenario, we have dropped 5 nodes in Netsim for vehicles, and all 5 vehicles are currently at the same location, and hence, due to overlap, only one is visible. As the simulation progresses, you will be able to see the others. We have further dropped 3 more nodes additionally for RSUs, and we have placed mobility.txt file in the bin folder of NetSim. You can observe NetSim Animator has buttons for running, pausing and stopping the simulation, and controls for speeding up the simulation and to step between simulation at different times. I will now parallelly run Sumo along with NetSim. Visualization in NetSim is much slower than Sumo because it needs to animate the flow of each packet, while Sumo only animates the vehicle movements. Also note that the precision of NetSim is 0.01 microseconds, whereas in Sumo it is in seconds. You can see that the movements in NetSim resemble movements in Sumo. It shows us the packet flow that happens between vehicles. Users may notice a vertical mirroring in NetSim, which means if a vehicle goes down in Sumo, it goes up in NetSim. This is because the origin, that is 0, 0, is at bottom left in Sumo, while it is at the top left in NetSim. Now we will try to match NetSim and Sumo by using the simulation step option. For this, I will restart the animation in both Sumo and NetSim. So I have paused the simulation in Sumo, and from now on I'll be using the step option to match the simulation in NetSim and Sumo. You will see that the vehicles will stop at this signal. So, to summarize, we first created the roads, traffic and vehicle movements using Sumo, and the output was given to NetSim. NetSim then simulates the network communication, routing, WLAN, etc. based on the mobility input given by Sumo. I would like to tell you that Sumo only provides the traffic road output while NetSim handles the entire network communication. Apart from that, we can view all features and functionalities of Manage in NetSim like packet trace, different metrics like network metrics, the link metrics, WLAN metrics, etc. We will now show you how different simulation experiments in VANETs can be run. The general use of a simulator is to keep all parameters except one constant and see the effect of the change of that one parameter on the output results. In the example we are about to show, we will be first varying the number of vehicles and in the second experiment changing the routing algorithm. In both the cases, we will be plotting throughput, delay and packet loss ratio against number of vehicles for each routing protocol. AODV, Ad Hoc On-Demand Distance Vector Routing, is an on-demand routing protocol for wireless networks that uses traditional routing tables to store routing information. DSR, Dynamic Source Routing, is a routing protocol for wireless mesh networks. Unlike AODV, it uses source routing instead of relying on routing table at each intermediate device. Let us now compare the results. Here is a summary of the results. Followed by this, we can observe graphs for throughput, packet loss probability and delay for different number of nodes and routing protocols. We can see that AODV has better throughput when compared to DSR, and also the packet loss ratio is higher in case of DSR. In both the cases, throughput decreases with number of nodes while packet loss increases with number of nodes. Packet delay also increases with the number of nodes in case of AODV. Please note that these results would depend on the speed of the vehicles, their movements or paths followed, location, etc. The following properties are available in NetSim. Application type, which selects type of application. We set application to generate traffic in NetSim. Transport layer, protocol for end-to-end delivery of packets like TCP, UDP. Network layer, basically for setting the type of routing. Routing protocols available are DSR, AODV, ZRP and OLSR. Physical layer, channel characteristics like path loss, fading, shadowing, BER versus SNR, modulation, etc. In addition, Wireshark packet capture tool can be used to capture NetSim packets for analysis. I will now open NetSim C source code that is provided along with the tool. As you can see, we provide source codes for WLAN covering 802.11a, b, g, n, AC and E. For MANET routing protocols, we have DSR, AODV, ZRP and OLSR. And for transport layer, we have TCP and UDP. We'll be showing more of the code and its working as we proceed. As an example, I will now show you packet structure in NetSim. This structure is a part of the packet.h file. This structure consists of variables like packet ID, which contains the ID of the packet, the type of the packet, which is either data or control packet, and we have a control data type in case the packet is a control data type, and variables for service type, packet priority and quality of service. The event time variable stores the event time at any point of simulation. And we also have variables for source ID, destination ID, transmitter ID and receiver ID. Additionally, we have variables for payload and overhead of the packets. And we have a packet status variable which has the value of either 0, 1, 2 or 3 with respect to no error, error, collided and dropped. And we also have structures for various layers which contains variables specific to layers like application, transport, network, MAC, PHY, etc. Now, we will correlate the NetSim's packet trace and event trace with the code. For this purpose, we first generate packet trace and event trace for the VANET scenario in NetSim. So I will rerun the network scenario that we have previously shown. I will now enable packet trace and event trace and run the simulation. I will now open the packet trace. This file logs a number of parameters as every packet flows through the network. As you can see, this file consists of several thousand lines. I will now filter packets from a specific source to a specific destination. Source ID 1 and destination ID 2. So this now shows all packets that were exchanged between device ID 1 and device ID 2 during the course of the simulation. So this contains various control packets and data packets, and the details of the intermediate devices that were used for the communication between the two devices, listed under transmitter ID and receiver ID. And it also has the arrival times at various layers. And it also lists the packet payload at various layers as overheads get added at each layers. Finally, it has the packet status which can either be collided, errored or successful. Now moving on to the event trace.